Okay, so in section 15.4 and 5, we talked about getting the concentration of hydroxide ions, right? The concentration, I said hydroxide, I meant hydronium. Concentration of hydronium ions, right? And I also pointed out that this is going to be equivalent to saying it's the concentration of hydrogen ions, right? In water, because these things piggyback on water molecules, which is what that is. So we're good with this, finding out what the pH, if you know the concentration of hydronium ions or hydrogen ions. Now, in a strong acid, right, what we mean is that the acid breaks up completely, right? So the concentration of HCl in water is the concentration of hydrogen ions. Did you hear that? Let me say it again. The concentration of HCl in water is the concentration of H+. Why? Because when these guys hit water, they all fall off, right? So finding the pH of a strong acid is the first thing that Tro starts out with in section 15.6. But it's going to be a greater challenge if we have a more complicated scenario. So let me take, for example, a weak acid. So let me say acetic acid, HCH3CO2, right? This is acetic acid. Well, I haven't left myself enough room to go sideways. This is in equilibrium with H plus and acetate, CO2 minus, right? So when you have some acetic acid in solution, you have some of this and some of this, right? And because K of this equation is not infinity or 0, you have some of both, right? That's going to be a challenge now. So that's what this section is about. This section is essentially about finding the equilibrium concentration of this. What is the equilibrium concentration of hydronium ions with a weak acid? Okay, this is going to look a lot like section 14.8. Okay, so we're going to set up our problems the same way we did with section 14.8. Take some weak acid, which I'm going to call HA right now. HA is going to be in equilibrium, right, with hydronium ions, which I'm writing as H+, so here it's H3O+, and A-, right? And we know that the K for this reaction is the products over the reactants, right? And so if you look up the K for this reaction, you should be able to figure that out, right? The same way we did in section 14.8 with other equilibria. This really is going to be Ka, right, for acids. But it's exactly the same math that we're doing in section 14.8. Okay, so let's look at one. Suppose we've got this acid, HA, which will be a general acid for now, and it breaks up into, this is my reaction, okay? If I have this, then we know that every mole, right, this is a 1, can you see it's a 1 to 1 to 1 ratio? So every mole that leaves of HA is going to become an H+ and an A-, right? So we set up our equilibrium the same way we did before. This becomes x squared over 0.10 minus x. And what we said in 14.8 is if x is small, then this is about the same as x squared over 0.10. Do you remember us doing that? This is super big shortcut, very big. This goes from being a quadratic to a not quadratic, which is much easier to solve. And it turns out oftentimes x is small. So that's what we're going to do here for the next couple practice problems. Okay? So first of all, let's do finding the hydronium ion concentration of a weak acid solution. So what we have to do is we've got to start here. We've got to say, all right, we know that HCN is in equilibrium with H plus Cn minus. Remember, I'm doing these things as the same. Am I repeating myself too much? Remember that. These I'm calling the same thing, right, for simplicity's sake. Okay, that's going to help some, and some of you may not like that. So I want to keep emphasizing that. Now we know that the Ka of this reaction is equal to the H plus Cn minus over the concentration of HCN, right? And this then, bam, is our hydronium ion concentration, which is where we get our pH. So if we just do an equilibrium concentration problem here, we solve this. That's exactly what this is about. So what we have to do is we've got to look up the Ka is Ka given in this question here? We've got to look that up. Got to look up the Ka of HCN, right? Because we're not given that. So I'm looking in the book on page, looking for HCN in the book, and I see it on page 611. Okay, so page 611, it's table 15.5. Says the Ka of HCN is equal to 4.9 times 10 to the negative 10. 4.9 times 10 to the minus 10. All right, so knowing that, now let's say what we're going to do, let's set up an ice table. Here's my columns from my ice table. HCN, H plus. I'm going to write the column headings down here. And writing is a little messy, a little latency in my pen. ICE. We know that HCN is starts out as 0.1, right? It starts out as 0. And we know it's a 1-to-1-to-1 ratio. See, can you see that? 1-to-1-to-1. So this is going to be minus x, and this is going to be plus x, and this is going to be plus x. Okay? And my equilibrium amount then is going to be 0.1 minus x. This is going to be x, and that's going to be x. So I know I haven't really left myself enough room here, I'm afraid. Let me come here with a different color to make it easier for you to see. Let me go with blue and say, I'm going to go kind of small here. If you're looking at this on your phone, I hope your eyes are good. I'll try to write real neat. K is equal to x squared over 0.1 minus x. Okay? So what I'm going to do is I'm going to assume x is small, in which case this then becomes x squared over 0.1. Man. And so now it's time for me to solve for x, right? So then x is going to be the square root of 0.1. Not sure why I've got some latency here, and times k, which is 4.9 times 10 to the minus 10. Sorry about the problem with my pen here. That's a 9. Okay? And that's the square root of that whole darn thing, okay? Can you see this is 4.9? This is a times, of course. If you don't know what that is, really you should pause the video and go back and figure out what I'm doing here. You should follow this math, right? You'll learn it much better if you're not just getting swept along. So can you see that that's 4.9 times 10 to the negative 11? Okay, looking for a calculator real quickly here. 4.9 times 10 to the negative 11. The square root of that. Just a moment here. Clear. 4.9. Clear. 4.9 times 10 to the minus 11 equals that. Take the square root of that, and that becomes 7 times 10 to the negative. Oh. Really? Really? I'm going to do that again. It's 7 times 10 to the negative. Maybe that's why it set it up like that for us, okay? Make it easy. 7 times 10 to the negative 1, 2, 3, 4, 5, 6. I'm going to check this, okay? That just seems too good to be true. 7.0 times 10. Got some latency in my pen here. Negative 6. That's what x is, okay? I'm going to check my math, though. That just seems 4.9 times 10 to the minus 11 equals that. All right. And yeah, that makes sense. Yep, that's it. Okay, probably could have done that in my head. I don't know. It just seems too easy. All right, so can you see that that's small? If I subtract that from 0.1, so my x is small approximation is good. It's not going to change that 0.1. So my answer then is going to be, can you see now, I know what x is. Wow, look at that. Beautiful. So really, my concentration of hydrogen ions is 7 times 10 to the negative 6. Now, what's wrong with my pen? 7.0 times 10 to the minus 6. I'm going to try and turn off some things on my computer here and see if that's the problem. Okay. All right, let me look at my notes here, make sure we're done with this problem. Yeah, that's it. I'm right. Beautiful. 7.0 times 10 to the minus 6. Okay, so that's example 15.5. We weren't asked to find the pH. We were only asked to find the hydrogen ion concentration. All right, let's move on and do one more example, and then I'll see my settings in my pen. All right, you know what? I should do that now. I got to get rid of some stuff off here. Maybe I've got too much open. Save. Quit. 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 Let's see if this helps. Let's see if this helps. Okay, finding the pH of a weak acid solution. So now we're going to do, we're going to find the pH. So I'm going to jump ahead a little bit because this looks just like the same problem we just did a moment ago. Let me go back to red. All right, so HNO2. No, this is not the same thing. This is HNO2. This is nitrous acid, right? It's in equilibrium with H plus nitrite, ICE, initial 0.2. Change. If this is 0 and 0, right, because it says that's all we've got, then this is going to be minus x, and it's a 1 to 1 to 1 ratio, so this is going to be plus x and plus x, 0.2 minus x, x, and x, so k is going to be x squared over 0.2 minus x. X is going to be square root of 0.2 k, right? If x is small. Okay, I've lost my little, can't change pen colors here. Okay, if x is small, that's what x is going to be. And so since this is my hydrogen ion concentration, right, then my pH is going to come right out of that. So let's come up here and say, I'm going to calculate this. I got to look up my nitrous acid pKa. It's probably also on page 611. Nitrous acid, nitrous acid is on 611. It's 4, the Ka is equal to 4.6 times 10 to the minus 4. I'm going to have to check my to see if the small x approximation is legit. So let's first of all calculate x. It's going to be, x is going to be, I'm trying to keep less notes on there, so you're going to have to pay attention. I'm writing less things out. We know that x is down here, right, is the expression for x is here, and the expression for k is here, right? So I'm just going to calculate those two. It's 0.2 times 4.6 times 10 to the minus 4 equals square root is equal to 0.00959. And here's the question now. Remember the x, I'm going to do that. I wish I could change my color down here. The x is small approximation. Let's check that, okay? Check it here in a box to keep things clean. 0.00959 over 0.2 is equal to, let's see, divide that by 0.2 equals, yeah, times 100. This comes out to be, and you're supposed to, if we're looking for a percent, right? This comes to be 0.04795. Wow, which is 4.8%. Okay, so it fits the x is small approximation, but barely, right? So let's go ahead and assume it. Okay, we're going to say, all right, we check mark. We're good. So this is x. It's that. Now, if that's x, then the concentration, I'm complaining too much, don't I? But this is killing me. This pen is killing me. H3O plus, this is a concentration, is equal to 0.00959. And so my pH is the negative log of that, right? pH then is, just a minute here, 0.2 log base 10, negative log of that, pH is 2.02. Okay? 2.02. Actually, I think I'm supposed to go out a third digit here. I forget now that rule. Am I supposed to go out a third digit? I don't remember the rule. Let's say 2.02. Okay? And there's my answer for this problem. Okay?